Okay, good afternoon, everyone. Thank you for joining us today. My name is Jatin, and with me here is Jaewon, and our other two group members are Aravind, who's outside, and Jeff, who's currently in Boston. And we are presenting hydrophobic aluminum for efficient refrigeration, and our advisor is Dr. Boshin Zhao. So the problem we're addressing here is refrigeration, because refrigeration is inherently a very energy-intensive process. In fact, just in the US supermarkets alone, it accounts for about 147 terawatt hours per year of energy consumption. And that's enough to power 10% of US homes. So reducing that by even a small amount can really reap huge benefits in terms of any energy consumption reduction, which will reduce greenhouse gas emissions. There's also an economic incentive for supermarkets as well, since an EPA report in 2015 reports that a 10% energy reduction would actually result in about 16% profit margin increase for supermarkets. So the point here is that even small improvements in energy efficiency can make large economic and environmental impacts. So the specific problem that we're approaching here is refrigerator frost buildup. So in a conventional refrigerator, the evaporator coils that cool the actual chamber of the fridge are susceptible to condensation and frost buildup. And once this frost builds up, it really reduces the heat transfer efficiency of the coils, so much so that a defrost cycle is required. And this means that the coils are heated up to remove the frost and to remove the water. So this really reduces the energy efficiency, and our goal is to reduce the amount of time that the refrigerator needs to be defrosted by as much as possible to increase the energy efficiency. So we collaborated with a company based in Boston known as Adaptive Surface Inc. And they proposed a solution to this problem, which is called SLIPS. So SLIPS is a slippery liquid-infused porous surface. It starts off with a nanostructured nanoporous template, which is then functionalized with a surface energy reduction coating. And then that is infiltrated with a hydrophobic lubricant, where once a liquid or water is put on the surface, it slides off since it only sees contact with the hydrophobic liquid. This technology was developed at Harvard University and is currently being commercialized for several applications at ASTI. So they actually took this technology and they applied it to, or they worked with an industry partner to apply it to real refrigerator coils in an industrial application. And they saw a 29% increase in energy efficiency over commercial refrigeration platforms. Now, the advantages of this system are that it's compatible with aluminum refrigerator coils, it's made using a simple three-step process, and lastly, it's self-healing and self-cleaning technology. However, there are a few drawbacks to using this technology, and it is that it uses a fluorinated system, so it's not a food-grade system. Second is it uses a very expensive lubricant and a discontinued surfactant, so it's not available in bulk anymore. It's processed in a high-temperature ethanol solution, which is obviously not a scalable process due to the flammability concerns. And lastly, there's a very high risk of washing the lubricant away, which would degrade the performance very quickly. So what we aim to do with our project was essentially address these concerns. So one of our requirements is to ensure that it is a food-grade system, so rated as the National Sanitation Foundation, H1, which means it's the highest grade of food grade out there. And second is it should have a comparable energy efficiency to the SLIPS benchmark that we proposed earlier. Third is that it should show a longer lifetime, comparable to the lifetime of a refrigerator. And lastly, it should be made in a commercially viable process, so ideally avoiding the solvents. And so that should be with regards to the materials and fabrication. So in terms of functional specifications, it should show delayed frost onset on the aluminum, should show a faster defrost, and should have a lower water retention after the defrost. So the second requirement is that the system should be processable in water so that it can coat an entire refrigerator coil. So our objective here over this project is to compare certain performance metrics between the benchmark and our proposed solution to use this as an analogy for energy efficiency performance. So to break down our project, we'll essentially start with the design that we start with, are all the materials that are proposed. Then we will narrow down our selection, look at experimenting with a few of these options, and lastly, choose a solution and verify that solution, comparing to our benchmark. So to start with the design, I'll go over the process of making our solution, or our SLIPS, and then we define the design parameters and the criteria that we use to narrow down our selection of materials. So the design is actually starting with an aluminum substrate that is then processed in boiling water to create a boehmite surface, which is an aluminum oxyhydroxide surface, which is naturally porous, nanoporous, and then after this, we functionalize it with a coating that reduces the surface energy of the substrate. And this is typically done in ethanol, but we were actually able to optimize this in water, which we will address later. And lastly, we add the lubricant via spin coating. So in terms of the two components we're looking at, the requirements for the lubricant are that it must be food grade, so NSF H1 grade. It must be compatible with the surfactant, must be thermally stable at low temperatures, must be durable, and relatively cheap. For the surfactant, we're looking at something that has a low surface energy, is compatible with the lubricant, is relatively processable in water, and lastly is also inexpensive. And so the three systems that we addressed are fluorinated, mineral, and silicone oil systems. So here is kind of the selection or the parameter space that we're looking at in terms of our materials. So we have the silicone, fluoro, and alkyl-based systems. And then we're looking at lubricants and surfactants for both. For the silicone-based system, we have, it's relatively expensive compared to the alkyl-based system and has a very small selection of food-grade options. The surfactant, once functionalized, actually has a very low contact angle, which means it has a very high surface energy. So this is already not ideal. For the fluoro-based system, we have some of the lowest surface energies among all these materials. And the lubricants have the best thermal stability out of all of them. However, the surfactant is incompatible with silicone and mineral oils due to its very low surface energy, and both these systems are extremely expensive. And lastly, with the alkyl-based system, they're cheap for the lubricants, and there are a wide selection of food-grade options. And the surfactant is relatively versatile because it can be processed in water. And so going on with our selection, we completely eliminated the silicone-based systems due to the inherent disadvantages. And since the fluoro-based surfactant is discontinued and wouldn't be available at a large scale, we eliminated that as well. So we selected fluoro-based lubricants, alkyl-based lubricants, and alkyl-based surfactants to continue our experimentation. So with that, I'll let Jaewon take over to talk about how we narrowed down our selection and tested our selection.
Okay. Now that we have a list of lubricants and surfactants to choose from, we need to find a way to narrow it down to find the optimal combination of the two. So the first thing we consider is the surfactant processing. So the hypothesis here is that the solubility matters when coating the bomite. So the solubility of the surfactant in the ethanol solvent can't be too high, otherwise the surfactant will just stay within the ethanol solvent, which means it won't coat the bomite. Also, if the solubility is too low, then the surfactant will wax up, will precipitate, and once again, it won't coat the bomite. So there is a middle ground where we tailored the alkyl chain length of the surfactant to choose the correct solubility, which is based on how easy it was to fabricate. There's also a second point here. Although most of our testing was done in ethanol because that was the original testing process done with the SLIPS benchmark, we also tested the alkyl surfactant in water, which greatly improves the scale-up feasibility of the device. Secondly, we also consider the lubricant durability factors. There's two components here as well, two factors. First is the surfactant compatibility with the lubricant. Now what this means is that we need to match the surface energies of both the surfactant and the lubricant to make sure that the lubricant wets the surfactant. So this is basically has to do with the retention of the lubricant on the SLIPS sample, where if the higher the compatibility with the surfactant, the lower the depletion of the lubricant. There's also a second, more physical factor, which is the viscosity of the lubricant, where if the viscosity of the lubricant is very high, then due to the lower flow, you're more likely to retain the lubricant. However, the trade-off is that because of the thickness, water or ice will actually be expelled slower than, say, a low viscosity lubricant. So to screen for these factors, we developed a small test, a pretty fast test, which we called the washing study, where we just fabricated a bunch of samples of different combinations of lubricant and surfactants. And these are mounted on a shower wall, and we were hosing it down for different time intervals. And this is to deplete the surface of the sample. And for various time intervals, after the washing was done, we took off the sample and mounted it on the goniometric stage. And over here, we pipetted 1.5 microliter droplets of water, about 10 of each. And we tilted the stage to 9 degrees and let it flow. And if any point where the water was pinned or stuck, we call that a fail. If the sample did not fail, we go back to the shower, wash it for another time interval, keep on testing until fail. Here are the results of the washing study. Now, it's important to note this washing test is nothing like what a fridge does in the back. But it's a quick way to screen for the lubricants, so it's actually quite valuable for optimizing the choice of lubricant and surfactants. So these graphs here show the lubricant retention volume on the y-axis and the amount of wash time on the x-axis. Eta here is the viscosity of the benchmark slips lubricant. This is hidden for confidentiality reasons. So on the left-hand side, what we did is we fixed a alkyl surfactant, and we made two samples, one sample with the fluoro lubricant, and another sample with the mineral oil. They have similar viscosities, which negates the fact that viscosity might have an effect on the left graph. And as we see, the mineral oil is much more compatible with the alkyl surfactant because it retains much more volume. On the right-hand side, what we did is we chose a lubricant of the same family, so similar chemical composition, and we varied the viscosity from eta to 90 eta. And once again here, we see a very clear trend where higher viscosity implies much better lubricant retention, so it's more durable. So from this study, we can see that the ideal solution or combination of lubricant and surfactant is you want an alkyl solution and a high viscosity mineral oil. Now, as I said before, this is nothing like an actual fridge, so we want to test this in a more realistic environment. So to verify the proposed solution, we partnered up with Harvard. They had a Frost-Defrost station, which was composed of a humidifier, a fan to disperse the mist, and a Peltier cooling plate where the samples were mounted on. And the test involved two cycles, a frosting cycle and a defrost cycle. In the frosting cycles, the samples were mounted on the cooling plate, and the cooling plate was cooled down to minus 10 degrees. And the relative humidity was set to 90%, which is quite high for what would actually be inside a fridge. But for accelerated frosting, this seemed suitable. This was let to dwell for an hour for frost to build up. After this, for defrost, the enclosure of this setup was opened, the humidifier was turned off, the cooling plate was also turned off, and the samples were just left to thaw. And all this process was captured by video coverage, as you can see here. So this part is the frosting process. Is it? Okay, I guess it takes a while.
Continue.
But the metric we want to find out here is the surface coverage. This is how we gauge the performance. On the left-hand side is the control of bare aluminum, and on the right-hand side is our proposed solution. It's important to note for this test setup, it can only fit 2 samples on the cooling plate. This is sped up very fast. The actual testing takes about an hour. Next, we'll show the defrost. Over here. And similarly, we noticed that from the frosting video, our solution has a much more delayed frost onset. So the surface coverage starts out less, and also as a defrost, it'll actually retain less volume, even though it seems like the bare aluminum defrosts a little faster. So to quantify the surface coverage, what we did is we used some image processing algorithms. We basically applied a Sobel filter, which is basically a gradient filter, to detect edges of the not only water but also ice, which have very different shapes. And then we enhanced the contrast to make it more visible, and then applied a median filter to smooth out any noise which was arisen from the Sobel filter. As you can see, this is the image processing algorithm taking place, and you can see it's fairly accurate to the actual video. And the equation for surface coverage is simply non-zero pixels, the sum of non-zero pixels over the sum of total pixels. Now these are the results of the defrost and defrost cycles. So we technically measured 2 types of samples, the original benchmark and our proposed solution. Now, as noted before, there are 2 controls here because the cooling plate can only fit 2 samples. So, and also the reason why there's 2 controls is because the thaw process in the defrost is not as controlled as the frost, because the thaw process you just simply open the enclosure, turn off the humidifier, and just let it open to the environment. So there's much more variability in the defrost. So in these graphs, we show the surface coverage versus the defrost time. And what's notable here is that our proposed solution matches up quite similarly to the original benchmark. It's slightly worse in the original frost coverage. But as it goes on, you'll notice that near the end of the defrost cycle, it actually retains less water than the control, which is quite important because fridges, when they actually operate, they don't only have one frost and defrost cycle. It's repetitive. So water from the defrost cycle from before will add on to the next frost cycle. It might accumulate. So it's important to minimize the defrost retention. So the benefit of this is that we found a mineral oil and alkyl system chosen based on maximizing or optimizing the surfactant processing, as well as lubricant durability. In addition, we meet the goal of being NSF H1 food grade for commercial use. And the system also shows delayed frost onset and lower frost retention as required. And this is the choice of materials makes it commercially viable. The mineral oil is much cheaper than the fluorinated oil, and also it's more processable in water. So it's likely to see that our proposed solution will meet the 29% or even exceed the energy savings that was done by adaptive surface technologies. So next steps that we need to do, because this is a completely lab scale testing, we need to optimize the process further for large scale production. And then we need to test the performance over multiple frost and defrost cycles, as we haven't done that before. And then we need to do actual field tests to recoat actual fridge coils with the lubricant. And from this, we can actually measure the energy savings, and then we can perform a cost analysis to see whether the investment in this technology will be beneficial from the return from the energy savings. Okay, so here are the contributions. Jeff's primary task was the washing studies and frost test in Boston. I did image processing and the other washing tests done. Jatin was responsible for data analysis and documentation. Aravind was responsible for experimentation and material acquisition. And we'd like to acknowledge Dr. Phil-Suk Kim from Adaptive Surface Technologies for providing us with the project idea, and Dr. Bo-Shin Zhao for being our consultant and an academic advisor. Jack Alvarenga for helping us with the frost and defrost setup at Harvard, and Jen Coggin for lab space at the NE Labs.